No, I live. Yeah, I mean, I'm in Berkeley. I know. Yeah, but I just came in today. We're actually we're staying in the South Bay, so so you're spending the year. Yeah. Mountain View, I mean, Palo Alto area. Yeah. I did successfully. Yeah. 5 and 8. So yeah, they're movable. Yeah, they're right at the stage.
Hey, what's up? How are you? Yeah. Sounds good. I'm excited. I'm excited for the mysterious abstract plus talk. Okay.
I wanted to get it. Okay, it's my pleasure to introduce my colleague at DT and friend.
Thank you. Dear friends. Yeah. All right. Anyways, yeah. So today I'm going to be telling you about recent work on Omniprediction. So this is joint work with Lunjia, who's a postdoc at Harvard, soon to start at Northeastern, and my awesome PhD student, Chutong, who is around to answer any of your serious questions about this talk. All right. Okay, so just a quick roadmap of this talk. Like roughly the first half, I will just try to tell you about all the words in the title and like why you should care about them and why I find them interesting. So we'll talk about omniprediction, we'll talk about single index models and multi-index models, and then we'll talk about our results. And then I'll tell you a little bit about our algorithm and our techniques, but that'll be like the second half of the talk. Okay. So omniprediction is sort of like a new spin on a traditional viewpoint of supervised learning. So the traditional paradigm is loss-based minimization. So basically, the idea here is, okay, so let me introduce you to the characters in this equation, which most of you are probably very familiar with. Here we imagine we have a bunch of feature label pairs, x comma y, coming from some distribution. And the only distributional assumption I'm going to use in this talk is that the x marginal is bounded in norm by 1. All of our results will hold in a scale invariant way. So I'm just going to write 1 to save myself some variables later on. Also, who are you trying to beat with your prediction? You're trying to beat a comparator class, for instance, linear functions or half spaces or something like this. So your goal is to compete against this entire comparator class script C. Okay, and then in what sense are you trying to compete with this comparator class? You're trying to minimize a loss function, right? You want to output a prediction that performs well on average over this distribution with respect to some loss. So here the loss is usually something like the squared loss or cross entropy or something like this. And then finally, your goal is to learn some predictor which takes features and then does pretty well on this loss. So in particular, if P actually comes from this comparator class script C, then we call it proper, and otherwise we call it an improper predictor. Okay, so this is like a familiar setup of traditional loss-based supervised learning. So omniprediction starts with the following question, which says like, what if you want to learn the distribution in a sense beyond a particular loss? So in particular, this has a lot of different motivations. One simple one is like, what happens if at training time you want to capture some information about your distribution, but you don't know what loss you're going to try to minimize in advance? For example, this could depend on exogenous factors like the market price on a given day, or other things that are impossible to know at the time of training. Alternatively, you might want to try to fit like multiple tasks with the same data. In particular, you might want to vary something like the weight of how much you care about false positives or false negatives, or in other ways reparameterize your loss using some parameter. Okay, and at a more like philosophical level, like we want to sort of capture this notion of like a fundamental truth about this distribution D of label feature pairs, which is independent of any particular loss function, right? So the way to think about this notion of fundamental truth is like through the lens of sufficient statistics. So the idea is, if I told you for every single point x what the actual like base optimal predictor was, like the actual conditional distribution of the label given the features, like that's sort of all you need to know to actually like do any sort of loss-based minimization, right? Because you can actually just simulate the flips at every point x and predict the optimal response. So the point is, like, if I can capture some information about this distribution, which is independent of any particular loss, I can use it to minimize multiple losses in the future. So this is sort of the starting point of the notion of omniprediction. Okay, so now I get to tell you what omnipredictors are. So this is a really exciting notion introduced by recent work of Gopalan, Kalai, Reingold, Sharon, and Weider, which says rather than target a single loss, we're going to try to learn something about the distribution which can compete with a wide family of losses simultaneously. Okay, so it's sort of like really moving beyond the loss-based supervised learning paradigm. Okay, so like what are the additional characters in this story? So now we have like this loss function family of all losses that we care about simultaneously, like learning the distribution against, right? And this you'll notice like one slight variation from this distribution from this definition from the previous definition, other than this for all L thing, which is that we're going to let you post-process the predictions P somehow. So once I've done my training and I've learned this predictor P, at test time, someone comes and gives me a loss, and I'm allowed to post-process my predictors in order to minimize the loss. So a few motivations for this. Even if I told you like the base optimal ground truth, P star X, expectation of Y given X, even if I gave you that, it would not stand alone be an omnipredictor. So this definition is sort of letting you do one additional step to the sufficient statistics you've learned in order to compete against the loss family. So the rules of the game for designing these post-processings is they have to be distribution independent, right? So like once I've learned my sufficient statistics from the distribution, I leave it at that. And then at test time, someone gives you a loss, and I don't use any information about the distribution in order to post-process. So sort of, it really decouples this notion of like, P is learning supervised sufficient statistics of this distribution. And then at test time, someone comes and gives you a loss, and you're allowed to respond according to the loss. So if there's any questions about this definition, please feel free to ask, because I know it's a lot to intake. Yeah.
You're gonna give us, I'm sorry.
Is there an expectation missing on that?
Yeah, so there's an expectation on it, right?
Like,
Oh, yeah, so that's it. Sorry.
So is it before the min or after?
After the
I mean, it should also be like C of X, right? C of X, Y.
yes, sorry. Yeah. I made a few typos, sorry about that.
I was just gonna say, like, you're gonna give us an example.
Yeah. Very soon. Yeah. Okay. But yeah, like the key things to wrap your head around is from the previous definition, all that changed was a for all and also a loss specific post processing. And one thing to note is that this is fundamentally an agnostic learning guarantee, right? We're not making any realizable assumptions about like the ability of the family C to fit the class with respect to a loss. Like we're trying to make this hold regardless of the actual ability of C to predict Y from X. I will get to the example very, very shortly. Yeah. So just to give you like a high level overview of like existing recipes for constructing these omnipredictors. So like at first it might be surprising that for large families of, yeah.
Just so that I understand.
Yeah.
So putting binary classification.
Yeah.
One loss could be logistic loss.
Yeah.
And the other loss could be like some squared loss.
Absolutely.
But in each case, you would have, if it's a squared loss, you'll have some different K.
Right.
And if it's logistic, you'll have like sign.
So the pipeline is like, I give you all the feature label pairs, you learn some P.
Yeah.
Then at test time, I'm like, all right, squared loss. Then you're like, all right, this function of P. And I'm like, okay, actually I cared about the logistic loss of this other function.
Yeah.
But they all have to be losses that take linear functions of C.
I will define the C and L I care about very shortly. Yeah.
Like, how do you judge if something is a good sufficient statistic? So how do you rule out solutions?
Yeah. So we'll give some sufficient conditions. Okay, cool. So I just want to give you like a lay of the land real quick before getting into specifics. So there are known recipes for omniprediction, but they're sort of complicated and abstract away, the core of the definition into like more complicated definitions. So this is sort of like the starting point of our projects. One of the first recipes given for omnipredictors was through this related notion called multi-calibration. And this is the original paper. So basically, multi-calibration, for those who aren't familiar, is this very powerful property of predictors, which says it agrees with the ground truth on a bunch of parameterized conditional distributions. And the point is, if you can parameterize a conditional distribution based on some function of C and L, and you like protect against all of these simultaneously, I'm being a little bit vague here intentionally, you'll get this guarantee. Okay. So it's like this reduction from omniprediction to this even more crazy notion called multi-calibration.
So, but what's the class that you're multi-calibrated with respect to?
Yeah, so it's like a family of weights.
Okay.
Defined. It's like a real valued notion of multi-calibration. It's not like a indicator version.
Okay.
I'm not going to talk too much about this because our goal is to move beyond these recipes.
But sorry, I gotta ask.
Yeah, for sure.
So usually when I think about multi-calibration, you have the set of classes being fixed in advance.
Right.
But here, is it not fixed in advance?
It's fixed in advance. It's parameterized by like the class you're multi-calibrated against is parameterized by like pairs C comma L.
Yeah.
So for like each C comma L, I give you like one conditional thing you need to be. Yeah. So it's kind of crazy, and
Okay.
I'll say a little. I won't say too much more about this recipe, except for the fact that there are known constructions of multi-calibrated predictors. They're all based on like reducing from agnostically learning some mixture of like either the comparator class or the loss family. And all I'm going to say about that is that for a variety of like very simple settings, this is known to be computationally intractable. So our goal is to like move beyond these reduction-based recipes and design more direct omnipredictors. Okay, so that was the first idea. And a recent work took a very important step in this direction by showing that conceptually, like much weaker conditions than multi-calibration suffice for omniprediction. So you don't need like the full power of multi-calibration. And the idea is they sort of abstracted away like what aspect of multi-calibration was actually being used and said, okay, if you can pass, like if your predictor passes a family of statistical tests parameterized by some combination of a comparator and a loss, then you actually turn out to be an omnipredictor. And like, what are these statistical tests? Roughly speaking, they capture this notion of your predictor satisfying two properties. One is called calibration. Calibration, roughly, like it's saying that, yeah, I'll give more concrete definitions later, but roughly speaking, calibration captures the performance against L. It says that like no L can really distinguish you and the ground truth. And multi-accuracy is this other notion that captures the dependence on C. Okay, so like if your takeaway from this is it still seems quite complicated, that was also my takeaway. So that was also a motivation for this work. Okay, so that is existing constructions for omnipredictions. Now I'm going to talk about a concrete setting where we're able to achieve much quantitatively stronger omnipredictors. So this is the setting that we're going to focus on in this work. Okay, so in this work, we're focusing on designing omnipredictors for single index models. So what does that mean? Single index models are essentially a semi-parametric model family where they posit that the conditional distribution of y given x is the following like semi-parametric function of x. Okay, so the parametric part is that I posit that the distribution has a preferred direction w. So I first project all of my x's in this one preferred direction. And the non-parametric part is that there's a link function, which is monotone. So it's sort of like, it's a 1D curve fitting problem along this one preferred direction. Right, so you might be familiar with the variant of this called a generalized linear model where I tell you the sigma you care about, for instance, the identity or logit. And in the single index model setting, the key difference is that sigma is not given to you in advance. So it's really like a non-parametric component of it. You want to like fit the best curve. So you want to learn like W and sigma simultaneously. Yeah.
So it's not like there's like some fixed sigma that's.
Yeah, it's like I give you the power to pick your favorite monotone function as well as your favorite direction. And you're trying to fit it using this semi-parametric. Yeah, so in terms of assumptions, I'm just going to make the assumptions that W is bounded by 1 for normalization purposes, and that sigma is bi-Lipschitz in monotone. These are the only assumptions we're going to use in this talk. Okay. So just a few fun facts about single index models. So it turns out that every link function sigma, every possible like monotone link function sigma you could think of, has a corresponding loss function associated with it. And this is called the matching loss. So it has this like integral formulation. A few notable matching losses are like if sigma is the identity, then you get the squared loss. If sigma is like logit, then you get the cross entropy loss up to the mild reparameterization. And a few like fun facts about the matching loss are if you just take a derivative, you'll note that the derivative at t, so t is like your prediction, is going to be the link function minus y. And this means that the matching loss is convex, right? Because the link function is monotone, so it has a monotone derivative, and therefore the matching loss is also convex. One key takeaway from this is if my prediction t is like sigma inverse of the ground truth. So basically, like if I want to take expectations at a given point x, what prediction should I predict to minimize the matching loss? Right. So if you set this equal to 0 and you take expectations over y, you'll find that the best possible prediction is to just unlink the Bayes optimal truth. So the takeaway here is that the minimizer for the matching loss is the unlinked version of the expectation of y, where the unlinking depends on which sigma you use to define the matching loss.
You fix the v here, the hidden direction.
Yeah. So you fix the direction w, and then for like each wx, you unlink y to.
Okay. Just a historical note that Manfred Warmouth was the first person to figure out to use the matching loss. Yes, because Matt.
I see. All right.
Yeah, that's one.
Even if you're just in the audience.
All right, cool. Just to go one step further, you can actually reparameterize the matching loss into a slightly nicer form called the proper loss. Here, there's a technical note that sigma should be 1-to-1 for this definition to work out. And basically, the idea is like, okay, the matching loss takes in two parameters, right? One is a label, and one is this unlinked predictor t, right? So note that t gets sent through the link function before it's treated as a prediction. So you should ask for like the linked version of this, where I give like an actual prediction b. So this is like a quantity in 0, 1, and it should be interpreted as like how close to y am I, according to this loss. And one nice thing about this is that every single sigma, if you go through these transformations, this loss ends up being proper. So in particular, if y is actually generated from a Bernoulli distribution, then the optimal thing to predict is just that Bernoulli parameter. So every sigma has a matching loss that under this reparameterization becomes a proper loss. So before telling you about omniprediction for sims, let me just tell you about learning sims. Yeah.
How do you get KL from sigma?
Oh, I'll explain. Sure. Oh, so sorry. KL. So if your prediction is a single sufficient statistic, KL is simply sigma inverse. Unlinking. Yeah. But more generally, it could be more complicated. Okay. So I have just one more slide before I get to tell you about omnipredicting sims, which is just like what happens when you care about learning sims with respect to a particular loss. Right. Okay, so if you assume that the model is realizable, so this is like the much simpler setting where you believe that there actually is a sim that exactly predicts things. There's a very simple algorithm called the isotron, which is known to learn sims in the squared loss. And the algorithm is like extremely simple. It's just alternating gradient descent and isotonic regression. We'll say more about that shortly. And one very nice property of isotron is that it learns proper hypotheses. So like the thing it outputs at the end of the day is actually of the form sigma w.x for some sigma in w. Okay, but we care about the more challenging agnostic setting, where the problem of learning sims in the squared loss is relatively less well understood. So a couple of recent works gave some significant improvements in this direction. But compared to the realizable setting, it's still like much more complicated. In particular, they require more distributional assumptions, such as like anti-concentration or sometimes anti-concentration, as well as like a mild amount of bi-Lipschitzness in one direction. And one thing I want to highlight is that like I would argue that these sort of constant factor learners are still a ways away from like truly understanding like what it means to learn sims in the agnostic setting. So in particular, like they say they're constant factor learners, but these constant factors are hiding large polynomial overheads in various other problem parameters. For instance, you could define like this parameter kappa, which is sort of like how well conditioned are your loss functions, and like you can check that while the sample complexity of one of these recent constant factor learners is near linear in the dimension, it's hiding like a kappa to the 44 factor in the sample complexity. So the question of like there's still sort of like this large separation between what we know about learning sims in the realizable setting and agnostic setting.
Just because I'm here, I just want to say we actually don't need more distributional assumptions. I mean, we just need.
Oh yeah, that is true. So I think the first work gets like a square root ops approximation, but using like much less assumptions, and then the second one gets like a constant factor approximation, but with many more assumptions. Yeah, that's right. Okay, cool. So now I get to the point of this talk. Our goal is to omnipredict sims. So what do I mean by this? Our goal is to compete against all matching losses for all monotone link functions simultaneously. So our goal is just take the previous definition of omnipredictors and make the comparator class linear functions and make the loss class matching losses. So our goal is to omnipredict sims in this sense. And I like, there's a very nice viewpoint of this goal when your sufficient statistic P is just a single scalar prediction, which is if you reparameterize this in terms of proper losses, what it's asking is that your prediction P, right, is doing as well on each proper loss given by sigma against any generalized linear model given by sigma. So the idea here is like, it's sort of flipping the realizable assumption on its head. It's saying like, if you care about fitting functions with sigma in particular, I will compete against all GLMs with that particular sigma. So for all sigmas, choose your favorite GLM in that sigma, I will beat you. That's the omniprediction guarantee for sims. And we're going to be able to achieve such a guarantee in the agnostic set. So any questions about the goal?
Did you ever give the examples Lou was asking about?
This is, oh, I guess this was the example. C is linear and L is matching losses. Sorry. Maybe I should have started with a simpler example or something. Yeah. Okay, so what happens if you throw the existing recipes at this problem, right? Like what happens if I just use these existing constructions based on like calibrated multi-accuracy and things like this? Basically, the only known like end-to-end construction I know for this problem was given by this earlier work of GHKRW, and he uses like roughly epsilon to the minus 10 samples to achieve this guarantee, which is like, polynomial in epsilon, but sort of qualitatively, it appears to be like a gap between, what this is and what one could hope for. Let me say a little bit more about this construction. The way it works is it repeatedly sort of like does an alternating minimization scheme to satisfy both of these conditions of multi-accuracy and calibration. And what ends up happening is both of these stages on their own end up being quite complicated. Like for calibration, you need to deal with all these like discontinuity issues that were talked about yesterday. And then for multi-accuracy, you need to sort of like repeatedly truncate the residual and then do some to not mess up the calibration. So it ends up being like quite a complicated recursive procedure. And a few other things about it is that the resulting hypothesis ends up being highly improper, right? Like it has no actual like resemblance to a single index model. It's just like this repeated like stubbed, bucketed, and like boosted hypothesis class. Another interesting thing about it is it has like a very large sequential depth. So in some sense, like you're not learning like all the stuff about the distribution at once. You have to like learn it piece by piece. So there's these questions of like, can we come up with like simpler hypotheses that are like more interpretable for this very simple like concrete model family?
So I think I'm confused.
Okay.
So here, what you're describing with like the multi-accuracy and the multi-calibration approach,
Yep.
In general, that's computationally hard because it is solving agnostic learning problems.
Right.
So here are you claiming that this GHKRW paper in the special case is computationally efficient?
Yes.
Okay.
Right.
And then,
here the problem is agnostic learning linear functions, which is definitely sample efficient.
okay. Sure. But the previous slide where you're talking about like Adam and others' work, this was like semi-agnostic or these types of guarantees.
So I was trying to draw a comparison between like the sort of like constant factor overheads you would have to pay in the squared law setting,
Okay.
compared to what you could possibly hope to, like the type sort of guarantees you can hope to get in the omniprediction setting.
Okay. But these are
Like it's like a factor of one. They are incomparable. Yeah.
I mean, there they make distributional assumptions.
Right.
And it's a different class of loss functions.
Absolutely.
But here you're restricted to things which come out of matching losses
Right.
of single index models.
So qualitatively, what I'm trying to capture here is like a tight characterization of what happens to learning sims in the agnostic setting.
Okay.
Right. Like in the squared law setting, you have to like give up on these large constant factors. I'm hoping to get like 1 times this plus epsilon.
Okay. Right. I mean, in part, that's because like the matching loss function is convex here.
Right. It's a different target, right? But it's like, what can you hope to learn tightly in the agnostic setting? Right. Cool. Okay. Yeah. Also, this large sample complexity. Okay. So, what was our approach to this problem? So this is sort of like a personality pick of like my type of the type of research I like to do. So sort of like before this project started, the lay of the land was like we knew how to construct omnipredictors in theory, and it works in like really like awesome like challenging setups, and you have like really strong provable guarantees, right? But when you want to like actually use this on a practical problem, people will ask like sort of like, okay, quantitatively, what are these guarantees, right? Like, what are your polynomial overheads in the runtime and sample complexity, and like, how does it perform on real data, right? I'm not claiming that the algorithms we design will like solve, omniprediction on your favorite like neural net example, but I think it's sort of like an important goal. Like, once we have these powerful TCS techniques to really bridge this gap for like practical realization, right? To like come up with the right algorithms and analyses in these tractable settings to make more of an impact on downstream applications. So this is sort of like one major motivation of this project. And here's our main results. Okay, so if you assume that the family you're trying to predict against is matching losses given by bi-Lipschitz monotone links, we give a much tighter sample complexity characterization. So it takes roughly beta squared over epsilon of the forest samples. And if you're willing to assume additionally bi-Lipschitz links, you get beta squared over alpha squared, epsilon squared. So roughly like condition number squared over epsilon squared. And one thing to note is like even if you want to learn the squared loss in the agnostic setting against linear functions, you need roughly 1 over epsilon squared samples. So this result immediately generalizes that to all bi-Lipschitz link functions with some poly blow up in the condition number. One other nice aspect of our algorithm is it runs in nearly linear time, which I'll talk a little bit about at the end. Okay, so just to say a little bit more about our omnipredictor construction, it has the following interpretable form. So in particular, like what are these sufficient statistics we return? Roughly speaking, we return 1 over epsilon squared single index models. So like when I give you an input function x, like the sufficient statistics I capture about it are really single index models. The only difference is that I need, a large number of them to sort of protect against this entire family. So it's not quite a proper omnipredictor, but it's getting closer. And perhaps like the most appealing part of this algorithm to me is that what does the algorithm end up being? It's actually just isotron with a custom isotonic regression solver and a bit of custom post-processing. So yeah, we call the end-to-end algorithm the Omnitron because of its newfound power to omnipredict.
Yeah, so jealous.
Yeah, Adam told me he liked the name, so pretty proud of that one. Yeah. Oh, Kosta said you guys actually wanted to use Omnitron for safety.
Yeah.
Anyways. Yeah, thanks for saving that one for us. Yeah, so a few like side remarks is that we get slightly stronger guarantees for settings where you have access to population level gradients. So instead of depending on like a probability 1 bound on the distribution, you can depend on like the second moment bound, which is a finer characterization. Another thing is if you care about one-dimensional omniprediction, we get like very close to proper omniprediction. So we give a double index model that suffices in 1 dimension. I won't say too much about these results in this talk, but a major open question of our work is like, can we understand like when it's possible to give proper omnipredicting constructions, even in 1D? And this is like getting remarkably close. So, all right. So I finally finished the overview. How am I doing on time?
You have like, I don't know, 7 minutes.
All right. I'll try to tell you about isotron a little bit and then skip the efficient omniprediction part. All right. So what is isotron? Roughly speaking, it's this picture. In a little bit more detail, it's literally the following algorithm. So for t iterations, all we're going to do is repeatedly find the best fitting curve in the current linear direction, and then update the current linear direction using a gradient descent step using the current link function. So it's like literally alternating isotonic regression, which is this picture, where you have like the 1D function that you're trying to fit using an isotonic function, and gradient descent. Okay. Yeah, so just a few notational things. This is like minimization in the squared loss sense. And this is, the gradient has this closed form that we can compute using a single step. Yeah.
Finally, one. So,
Sorry?
like, do I not want the 1W at the end of my learning algorithm?
Yeah, so like it'd be awesome if I could give you a proper omnipredictor. I can't do that, but I can give you 1 over epsilon squared sims that on aggregate protect against all single index models. Okay. So just a quick overview of how the realizable setting isotron works. So everyone's probably familiar with this equation. You first run regret minimization on the outer gradient sense stuff, right? So this is just straightforward online learning. The question is, how do you relate this to the squared loss in the realizable setting? Right. And the key observation, just skipping ahead a little bit, is that you can write this regret term as the sum of 2 components. And this is just kind of like adding and subtracting. But let me tell you a little bit about these 2 components. So the second component is where we're going to use the monotonicity assumption on sigma. Right, so in particular, because sigma is monotone and Lipschitz, you can charge. So what is this really? It's just sigma applied to these things. Right. So in the realizable setting, y actually is sigma w dot x, and then this thing is just sigma of there should be a sigma t. It's like the linked versions of everything over here. So because sigma is Lipschitz and monotone, once I do this linking, it dominates sigma itself. Right? Sigma is smaller than the unlinked version. So I get domination of the squared loss by the regret. Right? And the key other observation is this other line ends up being exactly 0 in the realizable setting, where you can use like exact isotonic regression. This is basically because the solution ends up being calibrated, which means that for fixed wt.x, the prediction is exactly equal to the outcome. So this cancels, and then once you condition on this, the whole thing is 0. Okay, so the story here is very simple. It's like we had this regret minimization outer loop. We decomposed into 2 things, one of which is 0, the other of which dominates the squared loss. So if I run it for long enough, like one of the squared losses is going to be good. That's like the entire analysis of isotron in the realizable setting. And I would strive for a similarly simple explanation of what isotron does in the agnostic setting. I think we got pretty close, which I'll explain on the next slide. Great, but any questions about this? Yeah, so what happens in the agnostic setting? So of these 2 stories that I told last time, where this one went away because of calibration and this one went away because it dominates the squared loss, the story is not quite so clean in the agnostic setting, but at least this term still works out. So the point is, like, by the exact argument used to establish calibration in the realizable setting, you can show that by KKT conditions of like isotonic regression, this term is still positive. So I can still get rid of it. This was observed in previous work. The real question is like, what happens to this leftover term, right? Like if I can't do these sorts of relationships between y and w.x, sounds kind of scary. And like a lot of previous works sort of argued about gradually improving the angle towards x. We're just going to tackle this term directly. Okay, so yeah. So enter the omni gap. All right, so what's the omni gap? So this definition basically exactly came out of the previous slide. If you have a predictor P, we define the omni gap to be the supremum over all pairs W sigma of this quantity. And what is this quantity? It's exactly the previous slide with the sim replaced by P. Right. So like our goal is to argue that this quantity is small. Yeah, so we're going to take a supremum over all comparators W and sigma here. So like because we're not in the realizable setting, we need to compete against all of them simultaneously. And one motivation for this definition is that the ground truth P, like if you actually predict P that is an expectation Y, the expectation of Y, this has 0 omni gap, right? Because if you condition on X, this is 0. If you take expectations, you get 0. So an interpretation is sort of like, if you have a small omni gap, then you pass many indistinguishability statistical tests like simultaneously, right? Each sigma W tells you like a single test between you and the ground truth. And if you're passing all of them, then you have small omni gap. That's the story. Okay, and it turns out that this definition sort of implicitly appeared in previous work, which is like remarkable how like tightly connected it is to the isotron analysis. Intuitively, like these two parts of the definition exactly capture these calibration and multi-accuracy components that I was mentioning earlier. So yeah, this will sort of protect you against the size of the gradient, and this will argue that like once I fix the prediction, these things are calibrated. Okay, and the key observation is that implicit in the prior work is the following theorem. If your omni-gap is bounded by epsilon, then P is an epsilon omnipredictor for sims. So this is essentially an entire like proof of population level isotron in the agnostic setting. So you like yeah, just sort of like mashing together the right definitions and KPG conditions to show that if you run regret minimization for long enough, you have a small omni gap, and therefore you get an epsilon omnipredictor. Okay, so I don't want to go over this proof, but here is just to convince you that the proof is not too long. This is the proof that epsilon omni gap implies epsilon omniprediction. It's not too crazy. Okay, and yeah, so what's the takeaway of all of this? Oh yeah, also like we use this to give our better 1D construction. Yeah. So what's the takeaway of all of this is that you can run the following simple algorithm in the agnostic setting as well. So basically, and this is working under finite samples as well. So the algorithm is as follows. We're going to approximate the isotonic regression solution from samples. We're going to take one stochastic gradient descent step, and we're just going to alternate this for t iterations. And what is our final output? It's just going to be the aggregate of all of the isotron iterates. So this is like the multi-index model part, right? Like isotron will produce a bunch of candidate link functions. We will just output all of them. And then finally, what is our like post-processing? We will just output the average unlinked prediction. So like at test time, you come and give me your favorite link function. I will just unlink all of my predictions and average them. And yeah, this is due to convexity of the matching loss. Right? Yeah, so this step ends up being quite straightforward once you have the right tools from stochastic optimization. So in whatever time I have left, I will briefly talk about implementing.
So the fact that you have this like 1/epsilon squared for like the number of WTs and your final omnipredictor is just the iteration.
Yeah, it's just the number of iterations. And you sort of need to like hedge against this one point with all of the points simultaneously to get the overall regret out. Yeah.
You have essentially no time, so.
Okay, cool. All right, I will just hype up one piece of the puzzle, which is that we, en route to this result, we gave a faster solver for bounded isotonic regression. So this is standard isotonic regression where you want to minimize the squared loss subject to monotonicity constraints, like they need to be in order. So this is AI equals 0 and BI equals infinity for everything. What happens if you have constraints? This exact problem sort of captures many variants of this Lipschitz, anti-Lipschitz business, and shows up in a variety of previous works. And previous works took n squared time and were inexact. We have a cool new solver that runs in n log squared n time. And Tian will tell you about it at his poster session. It's based on a recent work we had attacking the smooth calibration problem in nearly linear time. And that one ends up being like some piecewise linear function. We upgraded it to a quadratic. And the same techniques sort of work with minor modifications. I think it's good. Okay, yeah, so what else? Yeah, I think this is like very much like the starting point of a hopefully like a nice future program in terms of like constructing these omnipredictors for like concrete model families with end-to-end like efficient runtimes and sample complexities. So what other kinds of classes can we apply this to? We could imagine settings like regression rather than like predicting 0-1 labels. You want to predict real value labels. Multi-class classification. It has very similar themes to Han's talk from this morning, so I added this this bullet point. Also, this question of like proper omnipredictors is, I think, a major open question left by our work. Cool. Yeah, and this will be on archive hopefully soon. Yeah, thanks.
One really quick question on some of this sets up. I mean, really quick, could you take